Welcome back to chapter 15. In this chapter, we're going to be looking at random variables. Now, these are kind of like variables. A lot of the stuff that we're going to look at today is going to seem kind of familiar. Like you've done this before, kind of, and it and you have actually done this in previous classes, at least some of it. So, first of all, a random variable is a value. It's a number. So this is a quantitative thing, um, and it's based on the outcome of a random event. So a random variable is not going to be I draw a card and got a heart. It has to be a number. We generally use a capital letter. X is the first one. Y is the second one to denote the random variable. And then a particular value of random variable will be denoted by the corresponding lowercase letter, in this case, x. So um, like x would be the whole thing. Like we're going to do an example in a minute where it's you drawing a prize out of a hat or whatever. You're fishing for a prize. And then X, the capital X would be each individual or like the whole thing, like all of them, like the sample space. And then the lowercase x would be the specific ones. There are two types of random variables. There's the discrete random variables, which can have a countable number of options. So, I mean, we can actually count them, and they're generally speaking fairly small in number, like 5 things. They don't have to be. They could be more than that. Um, and then a continuous random variable is going to be a continuous variable where it could be that number could be like any number in between. So not just 1 and 2, it could be 1.7, 1.35, 1.24974. And so, and we treat them differently, kind of like the rules are all the same, but how we find some things is a little bit different. We're going to start out by talking about discrete random variables, but most of the year we'll actually be working with continuous random variables. So a probability model for a random variable consists of the collection of all possible values of a random variable and the probabilities that that the values occur. So being that we're listing out all possible values of a random variable, this is generally for the discrete random variables, because you're not going to list out all possible values for a continuous one. When you do, that's going to actually look more like a graph. Our normal curves are usually we deal with continuous random variables with normal curves. And again, that we'll deal with later on. And so, of particular interest is the value you expect for random to take on in the long run. So that's mu. That's the population mean. Sometimes we call it E of x for the expected value. Now, that can be misleading because the expected value might not actually be something that we could get. And we're going to see that here in just a second, because we're going to make a probability distribution here. So I talked about we're picking prizes, we're fishing, and each time you get like the little fish on a magnet, like at a carnival game at the fair, it has a prize value. We have 100 fish out there. In those 100 fish, 40 of them are $0. 30 of them are give you $1. 20 of them give you $5. 9 of them gives you $10, and there's one fish out there that will get you $100. So that's 100 fish, yes. All right, so our probability distribution. We have our random variable, and we'll have the probability of the random variable. So the random variable is going to be the amount of money that we could get. We could get 0, we could get 1, we could get 5, we could get 10, we could get 100. And then the probability of each of these, I made 100 fish so that this was going to be super easy. We have 0.4, 0.3, 0.2, 0.09, and 0.01. That's the probability distribution here. And so there's a couple ways that we could actually do this. The first way is the way we just did. It's what we pulled out. Now we could also do the amount of money that we win, because if we're at a carnival, they're going to charge us for this game. Like, let's say they charge us $2. In which case our x's, if it's the amount of money we expect to get out of it, the x's would be -2, -1, 3, 8, and 98, because the $2 that we pay in has to be taken out. And so those are two ways. We're looking at the same thing, but the numbers will be a little bit different on there. So back to the expected value. Now this is that mean. And so the expected value of a discrete random variable can be found by, I love this definition. We're actually going to do this. You'll see that it's not as disgusting as it sounds. But you sum the products of each possible value by the probability that it occurs. So we have this equation. And this is on the formula sheet you get on the AP test, by the way. All the equations that we see here today are on the formula sheet you get, so you do not have to remember them. This one, though, you're probably going to want to remember how to do, because the formula itself is not particularly user-friendly. But actually doing it really isn't that bad. Note, be sure to make sure that every possible outcome is included in the sum, and that you have a valid probability model to start with. What does that probability model be? What should it be? The probabilities should add up to be 1. If not, then you're missing something, and it's not a valid probability model. So here we have the same situation. I luckily remembered exactly what my numbers were. And so to find the expected value, what we're going to do is we're going to multiply each of these. So 0 times 0.4 is going to be 0. 1 times 0.3 is 0.3. 5 times 0.2 is 1. 10 times 0.09 is 0.9. Oh, that was supposed to be 10 times 0.09. And then 100 times 0.01 is 1. And then for the expected value, we're just going to add these numbers together. So the expected value of ours, we have 1 plus 1, 2.9, 3.2. So if we played this game over and over and over and over and over again, on average, we would end up getting $3.2 per time we fish. Now, I mentioned that expected value is kind of misleading, because you can't expect to get 3.2 ever. Like, that is not one of our options. But in the long run, if we average it out, that's what we're going to get. I said that the game costs $2 to play. In which case, if we had gone with the -2, -1, 3, 8, and 98, if it costs $2 to play, we could actually just subtract 2 from here. We're actually going to see that rule here in just a second. And so we'd expect to win $1.20 per game overall. So if we played it 100 times, chances are we'd be $120 richer when we were done than when we started. Now, the Carnival's not going to charge $2 if the expected value is 3.2. They would charge 4 or 5. Just because that's how they stay in business. That's how casinos stay in business. Yes, you might win, but the expected value is going to be less than the cost to play. So that's the law of large numbers thing. In the end, the house is going to win. You might have some successes in the middle, though, but other people aren't going to. Or maybe you're losing, but other people are going to win, but the house comes out ahead. because they've done this math. They know what the expected value is, and they charge a little bit more. In order for it to be called a fair game, the expected value would equal the cost. So a lot of times, like AP type questions, they'll say, how much should it cost to play this game if it's fair? And the answer to that would be $3.20, because that's the expected value. Now, a lot of people think fair and the consumer side, and they're like, well, $20, that way you win. It's like, no, fair means it comes out even. So that's how to find the expected value. Again, the equation itself is kind of unpleasant, but you just multiply these guys, multiply, and then you just add. That's all it is. And so that's the center of the distribution. Now there's the spread. So for the standard deviation, which remember we talked about that way back when, random variables have standard deviations too. The first thing we do is we calculate the variance. Now the variance, we're going to go x minus the mean squared times the probability. Can't remember if I put another slide at the end of this. We're going to do it right here. And then, no, I think I did. I think I put a slide for us to do this. All right, so it's the x minus the mean squared times the probability, and then you add that together. And then standard deviation is the square root of that. So, yes, all right. So we had our mean, the expected value was 3.2. So we're going to have x minus 3.2 squared. So this would be 3.2 squared. This would be 2.2 squared. I know 1 minus 3.2 is actually negative 2.2, but we're squaring it, so that doesn't matter. 5 minus 3.2 is going to be 1.8 squared. 10 minus 3.2 is going to be 6.8 squared. 100 minus 3.2 is going to be 96.8 squared. So we're going to find those numbers, and then we multiply to the 0.4, and then we add those together. So as you can see, this is going to be a little bit irritating. 3.2 squared equals, I got 10.24, and then we multiply that to the 0.4 to get 4.096. Plus, we do the same thing, 2.2 squared is 4.84 times 0.3 is 1.452 plus 1.8 squared is 3.24 times 0.2 is 0.648 plus 6.8 squared is 46.24 times 0.09 is 4.1616 plus 96.8 squared, not doing that one in my head, that's for sure, is 9,370.24 times 0.01 is 93.7024. And now we add all those together to get the variance of our random variable. So we have that 93 plus 4.1616 plus 0.648 plus 1.452 plus 4.096 is 104.06. That's the variance. Then the standard deviation, just like the other standard deviation, is going to be the square root of the variance. So it's just sigma of x, and it's the square root of that number is 10.2009. So we'll go 10.2 is the standard deviation. So that's how you could find it by hand. Generally speaking, we don't find it by hand like that. I mean, we do, but we use our tables. Put them into the tables in your calculator, and you can do all these using, or not the tables, in the lists in your calculator. Same place you put data, list 1, list 2, and you can do this. You can do list 1 minus 3.2 is something. Then square that one is that. And then you multiply it to the other list, and then you find the sum of that. So you can do all of this using the list features. And the equation, though, if you forget, and I mean, yeah, it's a little bit time consuming, it's a little bit obnoxious, but really isn't that tough. I mean, it's just computation. You can always do it by hand. The formula is given to you. It's on the formula sheet. It's just irritating. Generally speaking, on the AP test, yes, you will be finding an expected value at least one time in multiple choice, and sometimes it's one of the free response questions too. Usually question 3 or so is going to be about probability, and it'll have a table, and part of the question is to find the expected value. Now, it might be asking what price to charge to make the game fair, and so it might have like a little twist. It might not say find E of X, but that's there. Very rarely do you have to find the standard deviation or the variance. However, you will need to be adding them together, and that we'll see here in just a second. So the means. So adding or subtracting a constant from data shifts the means, but does not change the variance or the standard deviation. So here, the x plus or minus c. I mentioned this before. We had f of x or e of x, and then we subtracted 2 because it cost $2 to play. And so we were able to just subtract the 2 from the expected value. It actually works out that way. It factors out and comes out mathematically, and it's perfect. If we did the same thing for the variance talks about the spread. If you subtract or add, you take that same exact shape, you just slide it horizontally on the line, and the variance is the same. So notice that linear that linear transformation, the adding of a number, doesn't change the variance at all. And then multiplying does kind of the same thing. If you multiply all the numbers, like let's say, all right, we just want to double the prize money. So instead of 3.2, it's now going to be 6.4. We just need to multiply by 2. The variance gets that squared, because remember, the variance is a squared value. Funny thing is, the standard deviation, it's the square root of the variance. Well, when we take the square root of this, the a squared just becomes a, and the square root of the variance is a standard deviation. So when you multiply by a number, so if we multiplied by 2, the standard deviation would just be 20 point whatever it was. And so, in general, the mean of the sum of the two random variables is the sum of the means. So that means that if you're adding or subtracting them, you just add or subtract your means. So let's say we have 2 different games. We have this one that had 3.2, and we had another one that had 1.7. If we played both of them, we would expect 3.2 plus 1.7. So 4.9. If we wanted to subtract them for some reason or another, because that made sense in this situation, we would subtract. We have 3.2 minus 1.7. So you can just add or subtract, and it adds or subtracts the expected values. The variances add. Now, the variance is a spread. It does not matter if you add or subtract your random variables, the spread will increase. And so, even if you add or subtract, you always add the variances. The variances add. Standard deviations do not. you have to square them, then add. So variances add, standard deviations do not. And there is the most wonderful, wonderful description that I have ever seen in this book on why that is, and that is called it was called like the Pythagorean theorem of variances or something like that. It had the standard deviation of x, and this was the standard deviation of y. And so the standard deviation of both of them, it's the Pythagorean theorem. You have to that was supposed to be a y, but you need parentheses. Um, so you have to square them, add them together, then you can square root to get that standard deviation. So again, I've never seen it described like that before. It makes so much sense that way. Anyway, we'll use these in some future chapters because we'll be looking at proportions of two means. We'll be comparing two different means, and so these will come back. Continuous random variables, they're on a range, and when we look at those, we look at the probability distribution is going to be a graph. It's going to be that density curve, the thing where we have the shading underneath the line, underneath the probability. A lot of times we're going to be dealing with the normal curve because dealing with geometric curves is boring and we don't do that in statistics too much. But we deal with the normal curve, which gets us back to the table A and all that stuff we've seen a couple times this year. It's going to come back over and over and over again. The end of the year, as I've mentioned before, it's going to be a lot of table A and then a couple other tables back there too that are very similar. And when we're looking at these, we look on for a range. Like, so we're not going to get the probability that x equals 2. We're going to get the probability that x is between 2 and 3, or 2 and 2.5, or whatever these values are. And we find the area here. Anyone who's already been through calculus is having some PTSD flashbacks with integrals and, oh, I don't need to find the area under the curve. No, that's true, because the tables found it for us, so we don't have to find those values. And so, but all of the formulas and stuff, everything that we've had for the discrete random variables work exactly the same for continuous random variables. That does not change. And when two independent continuous random variables have normal models, so does their sum or difference. So if we add two normal things together that are independent, which is generally going to be one of our assumptions so that we can do this stuff, the sum or difference is also going to be normal. So we'll still be able to use table A because that requires the normal curve. And yep, that was that. So what types of things can go wrong? Well, probability models are still models. That doesn't say this is a definite thing, but it gives predictions. And then always question your probabilities. Question the assumptions, question everything basically. And then if the model is wrong, so is everything else. No good statistics can come from bad data or bad models. So make sure that the probability model is reasonable. Make sure it adds up to 1. That's a big one, especially a lot of times a multiple choice question is this a valid probability model? Somehow or another it asks that question and they won't add up to 1. So no, it's not valid. Don't assume that everything's normal. So we do have to definitely show that that is something. We can't just assume that it's normal. We have to do some sort of a check on that, normal probability plot, things like that. That's not so much this chapter that we've done in the past. We'll do a lot more. And then watch out for variables that are not independent. You can add expected values for any two random variables. So even if they're independent or not, you can still add them. But the variances, that equation where you just add the variances, is only for independent random variables. Yes, you can add variances for, or combine variances for non-independent variables. The formula is unpleasant. Um, it you add them, then you have to subtract off a bunch of stuff. It is not a fun time, and it's not really something that you're going to have to worry about. Um, don't forget, variances of independent random variables add, standard deviations do not. Remember the Pythagorean theorem there. You have to make them variances, so square them, add them together, and then square root. Um, and they add even when you're subtracting the two random variables. They still add, because whether you add or subtract, the spread is going to increase because you have more stuff that you're working with. Then don't write independent instances of random variable with notation that looks like they're the same variables. So make sure that you don't want p of x equals p of x equals. Sometimes you could have like p of x equals 1 is 0.4. No, it was 0.3. And then p of x equals 5 was 0.2. So you could do it that way. That's a good way of showing which one you're looking at. And so what have we learned? We know how to work with random variables. We can use a probability model for discrete random variables to find the expected value and standard deviation. The mean of the sum or difference of the two random variables is just the sum or difference of their means. So you can just add the expected values or subtract the expected values. And for the independent random variables, the variance is the sum of the sum or difference is always the sum. Again, sum or difference is always the sum. Those are the equations that they have you use more. They'll say that, oh, this standard deviation is this standard deviation is this, and this expected value is this, and this expected value is this. What if you subtract these two? Find the new expected value and standard deviation. So you have to subtract the expected values and add the variances, not the standard deviations. The sums or differences of normally distributed variables also follow normal models. So you have two normal things added together, the result will be normal. And then some AP tips. So finding the expected value is a common multiple choice question. And as I mentioned, it also shows up in a free response question as well, fairly often. If you're creating a probability model, make sure your probability is summed to 1. And make sure you think about independence before you find the standard deviation of the combination of two random variables. Because if they're not independent, it doesn't work. And so if they were having you do it, you would have to make that assumption. You'd have to actually state that. And generally speaking, give some sort of a reason for it. Like, and since it was stated in the problem that they're independent, we can use this formula where we add the variances. So this was chapter 15 on random variables. We'll be looking at it throughout the week, starting out with the expected values and finishing up the week with the variances and stuff like that, doing some practice. And so I will see you in class. But until then, keep working problems, keep asking questions, and as always, happy mathing.